We solve this by using what's called a bounding volume hierarchy, or BVH. Essentially, we take triangles in the scene and, using their 3D coordinates, we divide them into two separate boxes called bounding volumes. Each of these boxes contains half of the triangles in the scene. Then we take these two boxes with their 1.5 million triangles and divide them again into boxes with 750,000 triangles. We keep on dividing the triangles into more and more progressively smaller pairs of boxes for a total of 19 divides. In the end, we've separated 3 million triangles into a hierarchy of 19 divisions of boxes, with a total of 525,000 very small boxes at the bottom, each with around 6 triangles inside. The key is that all of these boxes have their sides aligned with the coordinate axes, which makes a far easier calculation. For example, if we have a ray in two axis-aligned boxes, finding whether it hits box A or box B is just a matter of finding the intercept with the plane of y equals 6, and then seeing whether the intercept coordinates fall between box A's bounds or between box B's bounds. Then we do the same thing inside box B, but using the axis-aligned coordinates of the two smaller boxes inside of it. For a scene of 3 million triangles, these 19 box-divide branches form a binary tree or hierarchy, hence the name bounding volume hierarchy. At each branch, we perform a simple ray box intersection calculation to see which box the ray hits first, and then the ray travels to the next branch. At the very bottom, once a ray finishes traveling through all the bounding volume branches, which is called BVH traversal, we end up with a small box of only 6 triangles. We then do the ray triangle intersection calculation that we mentioned earlier with just these 6 triangles. As a result, BVH trees and traversal reduce tens of millions of calculations down to a handful of simple ray box intersections followed by 6 ray triangle intersections.